Hi there. Welcome back to the Garuda Podcast. I hope all of you enjoyed the first three episodes of the podcast, and I hope you continue to watch and support the Garuda Podcast. Just before we begin, I just have a humble request to all of the viewers to please subscribe to the channel, as this will enable me to further grow the podcast and invite more and more guests on the show. Today's episode is going to be a little bit different. Within the first three episodes of the podcast, I was quite fortunate to have a conversation with three different pilots, whereby we had a conversation about the airplanes they are currently flying, their advice to young aviators, and their perspective on the field of aviation. In today's episode, I was quite blessed to have a conversation with a quantum engineer. Now, all of you might wonder, what does quantum engineering have to do with aerospace engineering or aviation? Well, it is speculated that quantum technologies, such as quantum radar, will be used by air forces around the world to further enhance their stealth capabilities. For instance, it is speculated that the F-35, manufactured by Lockheed Martin, and the B-21 Raider bomber, which is currently in development by Northrop Grumman, will make use of quantum radar within these military aircraft. Additionally, it is also said that the DRDO, India's premier research agency for its armed forces, has also been conducting research within the development of quantum radar. In today's episode, I got a chance to interview a quantum engineer who was able to talk about the development of quantum radar and about the topic of quantum sensing, which basically holds the fundamental principles for which by quantum radar works. My guest here took the time to prepare a presentation on the basic principles of quantum sensing and the principles by which quantum radar would work. I hope you enjoyed this episode of this series, and I hope you continue to support and watch episodes of the Garuda Podcast. Let's begin. Yeah, thank you so much, Abdullah, for coming on the fourth episode of the Garuda Podcast.
Yeah, yeah,
And I'll just begin with a short introduction about you.
yeah.
So my
Great.
next, yeah. So my guest here is Abdullah Kazi, and he is a quantum engineer. He has been working within the field of quantum sensing, and his key research lies within theoretical and experimental physics, and his particularly it's within the field of applied physics and thermodynamics. And his research or areas of interest are particularly around areas of particle physics. He is also really passionate about research within quantum physics and quantum computing, which is going to be the main focus of today's episode. And Abdullah currently has a bachelor's degree in applied physics and mechanical engineering, and he hopes to continue working in this area and conducting further research within applied physics. He also has attended the IBM Summer School for Quantum Machine Learning and Quantum Simulation. And Abdullah is currently working with IBM. So thank you, Abdullah, for giving me your precious time.
Yeah, yeah.
And
Thank you
yeah,
for
we can
inviting me to the podcast. Yeah,
yeah, we can begin. So before we delve into the quantum sensing as applications, my first question just for you is like, what made you consider a career in physics? And like, could you just describe how you started working in quantum physics?
yeah. So to start with, I was particularly enrolled into my majors, mechanical engineering. So during my second year of engineering, I was involved into a lot of theoretical research. Like I was involved in working on classical mechanics, and I was like studying thermodynamics and statistical mechanics. So I was majorly inclined to quantum physics and quantum mechanics at that time. And I found out that quantum physics was very much different than classical mechanics due to the probabilistic nature of quantum mechanics, and also due to the various type of technologies that were emerging out of quantum computing at that time. So it was through my curiosity for the subject, and like to venture further into this field, I was particularly interested in the theoretical aspect of quantum computing, like quantum field theory and ADFS and CFTs, and working on gravitational wave dynamics and get something on astrophysics. So there's a lot of things which I was interested back then, which made me more inclined towards quantum physics and quantum computing. So that is how I ventured into quantum computing, due to my passion and my curiosity for the field. So that's about it.
Yeah. So, like, just out of curiosity, could you maybe talk about any of the courses you have taken in university which kind of focus on quantum physics or quantum computing
Yeah,
or any other quantum technology course?
yeah. So I have taken around a lot of courses which are based on quantum computing and quantum physics. So one of them is Qubit by the coding school, which is a much recommended course. So it covers all the part of quantum mechanics, and it covers all the basic things which are required to study quantum computing. And after that, I was enrolled in a course from Q World, which is called Qbron. So it is also a good course to start with, and it covers majorly the mathematical part of quantum computing, like linear algebra, the prerequisites of quantum computing, and all that stuff. And for a university course, I did a course by University of Basel called Spin Qubits, in which I was exposed to like the mathematical equations of spin systems, spintronics, and then I did a course by IIT Madras on quantum materials. So the course was about quantum materials, the diamond qubit, different type of qubit selection, and qubit modalities. So yeah, so I did a couple of courses in quantum computing, and also did a university course on quantum computing, which is involves uh, application of quantum computing in quantum sensing and quantum machine learning. Yeah, so that all these courses I have done in the past, and currently I am also doing a new course by University of Basel, which is based on spintronics, like based on the quantum spin of the quantum materials. So yeah, I'm currently enrolled in that course.
Okay. So, so talking about like quantum physics, like I'm most excited about just like the applications of quantum physics, like quantum information and quantum sensing, which is kind of like the main topic of this podcast. But quantum information, not yet, but eventually it is predicted that it will help solve problems within the field of medicine and quantum sensing. Hopefully, in the near future, it will help solve problems within, like it will not necessarily help solve problems, but it will have applications. Some of its applications will be like quantum radar. Like, what are you most excited about with regard to the applications of quantum physics?
Yeah, so I guess quantum physics has a wide range of applications, like including quantum cryptography and quantum sensing, quantum teleportation, and quantum imaging. And there's a lot of application which can be implemented in modern days, modern day science and stuff like that. So the major thing which I am excited about is the application of quantum sensing for military and defense purposes. So I guess it uses the properties of quantum entanglement to create radar signals. So quantum sensing for me is a very new and very much different field than quantum computing, which will be like impacting most of the market scenario in the future. So I guess quantum sensing has a wide range of potential application, some of which includes medical imaging, like quantum sensors can be used in magnetic resonance imaging to detect subtle changes and in the body that may indicate the presence of diseases. And quantum sensing can be used for mineral exploration, like quantum sensors can be used to detect mineral deposits and other natural resources buried deep underground. And quantum sensing can also be used for navigation to create highly precise navigational systems that can operate even in the absence of GPS and signals. And quantum sensing can also be used for industrial monitoring, like quantum sensors can be used to monitor the performance of machinery and equipment, like to detect faults and optimize the processes. And quantum sensors can also be used for defense and security, like which I told you earlier, like for detection of chemical and biological nuclear weapons and nuclear threats. Like it can be used for that purposes, as well as sensing can be used for astronomical and astrophysics purposes, like used to detect the faint signals. It can be also used to detect comets or asteroids or stuff which is a threat to which is a threat to human civilization. And it can also be used to detect faint signals from distant objects in the space, such as gravitational waves and dark matter. So I guess quantum sensing has a huge potential to revolutionize many fields by providing high, precise, and sensitive measurements of physical quantities that are like difficult or impossible to detect using the traditional sensing technologies.
Okay. And like, what type of work are you currently involved in? Like, and like, where are you currently working?
Yeah,
So,
so majorly my work revolves around theoretical research, basically, and I worked as a system IBM Z system advocate and a mainframe advocate for IBM. So my work was around facilitating the IBM Z computers, the mainframe computers. So I guess IBM mainframe has released the IBM Z16, which is now currently in the market, which will be used to revolutionize and will be used to uh, like work on the quantum cryptography part, like which we will be using the mainframe computer to work on the uh, quantum safe cryptography. So that is where my work is currently right now, and I'm also working towards quantum field theory and string theory and supersymmetry and computational fluid dynamics, multiphysics simulation, quantum thermodynamics, and like things which are at intersection of applied physics and quantum computing. So I am working at the intersection of both these fields. So yeah, like but my major inclination is towards theoretical and experimental research. Like
but could you just briefly talk about like just briefly talk about like how doing research in like quantum field theory and like CFD and stuff like that?
yeah, so actually I wanted to emphasize more on what is a quantum field theory. So I will just go give an overview of actually what is key quantum field theory and computational fluid dynamics. So quantum field theory is a theoretical framework in physics that combines the classical field theory, special relativity, and quantum mechanics. So it is a kind of a mathematical language for describing the behavior of subatomic particles and the interaction between them. So in KFT, particles are represented by field that are permeated all of because of space and time. So these fields can be thought of being made up of many individual particles, which can be created or destroyed as a result of interactions with other particles. So the behavior of this field and particle is described like by using a set of mathematical equation which is known as Lagrangian. which describe and specifies the dynamic of the system. So the thing is that the Lagrangian mechanics is part of classical mechanics, and most of my work is revolved is inclined and revolves around classical mechanics and stuff like that. So one of the key features of quantum field theory is that it incorporates the principle of quantum mechanics, which allows the calculation of probabilities and the prediction of the outcomes of experiments. For example, this has led to the development of many important theoretical predictions. Like, for example, you might be knowing about Higgs boson, the God particle. So it has led to the development of many kind of things, which are which is a part of the ecosystem and part of the universe. So quantum field theory is a fundamental framework in which modern physics is used, and it is used in many areas including particle physics, condensed matter physics, and high energy physics, and also cosmology. So it has led to many theoretical prediction and experimental discoveries, and it is a very much active part of research right now. Like, many researchers and scientists are working on quantum field theory as of now. So it's a very interesting and a great part of research which is currently going on. And talking about computational fluid dynamics, so computational fluid dynamics is a part of uh, multiphysics simulation, and computational fluid dynamics also part of applied physics. So computational fluid dynamics a very broad term, and computational fluid mechanics is a what I can say. It's like not related to quantum computing, but uh, is a branch of what I can say, a branch of fluid mechanics mm, that uses the numerical analysis and algorithm to solve various problems in fluid mechanics. Like, the one problem is Navier-Stokes equation. So Navier-Stokes equation is a billionaire problem right now, which is which is unsolved. So anyone who solves the Navier-Stokes equation is eligible for a prize money of around 1 million US dollars. So like, many kind of research is going on right now. So actually it involves the use of computers and computational tools to simulate the behavior of fluids, like the liquids and gases, and their interaction with the surfaces or structures. So by solving the governing equation of fluid motion, we will be like able to like check out the turbulence of the fluid, and we will be able to calculate the Reynolds number of the fluid. So CFD involves a very much theoretical approach to solve the computational fluids. Like, we can use partial different equations to solve the heat wave equation, and there's a lot of things. Like, we can use the finite element analysis equation, and CFD involves a lot of steps. Like, first is the pre-processing. So pre-processing involves the simulation of domain, like defining the geometry and specifying the boundary conditions and the initial conditions. And after that, we need to check the numerical methods. For example, in numerical methods involves various kind of methods. Like, I can say that uh, discretizing the governing equations method is also there. So I guess there's a lot of method which is used in computational fluid dynamics, which can be exponentially like used for quantum computing as well. So we can use quantum technologies to exponentially increase the rate of rate of execution of fluid dynamics to solve the computational fluid dynamic equation. For example, we can use variational quantum eigen solver, the VQA equation. We can use the hybrid quantum classical algorithms as well, and we can use error correction as well to solve computational fluid dynamic equation. So yeah.
So I just had one last question before we delve into the specifics of quantum sensing. So, like, do you just know why there's like a deep fascination or attraction towards this, like the study or research of quantum physics? Like, in any Marvel movie, like they just attach the word quantum to anything. Like even in the recent Ant-Man movie as well, they were, like quantum physics or just quantum in general. It was like a major theme in the movie, and it's like a huge buzzword, and everybody's really just genuinely excited about research in quantum physics or quantum field theory or quantum computing. Do you know why that is? Or
Yeah, yeah. So actually, the thing is, I guess there's a lot of hype behind quantum computing. So regarding that, there's a lot of hype surrounding quantum physics and quantum computing. I know because of the Marvel movie and all that stuff. So one reason for that hype around quantum physics is that it provides a why, because it provides a fundamentally new way of understanding the universe. So, which has led to many important theoretical predictions and experimental discoveries. For example, one example is for quantum physics explain phenomena such as superposition, like entanglement and quantum tunneling, which has no classical analogs. So, which can lead to development of new technologies. So, quantum computing and quantum physics is somewhat a new area of research like which people don't know about. So that is why it is very much hyped, and people are very curious about it. And quantum computing in particular has attracted a lot of attention from the industry point of view. And because I think it has the potential to solve problems which are very much hard for classical computers, such as factoring large numbers and simulating complex quantum systems. So this has important implications for quantum cryptography as well, because quantum computers have like I guess someone has predicted, or they have claimed that quantum computers could break many of the currently used encryption. Like there are many methods for that, and also I guess quantum computing can be used for drug discovery, material science, and which in fields where classical computers like have a limit or a disadvantage. So overall, the hype around quantum physics and quantum computing stems from the potential to solve some of the most challenging problems in science and engineering, like STEM. So, and the possibility of unlocking new technologies that could transform our world. So I guess the hype behind quantum physics and quantum computing is all comes from the questions which are been imposed on classical computing. Like quantum physics and quantum computing comes like emerges from where there is limitation on classical computing. So that's why a lot of people are interested in quantum physics and quantum computing, because they don't have any answers for that in classical computing. So I guess that is why the hype is very much built around quantum computing. And to tell you that apart from the hype, like I just wanted to tell you that a lot of people don't know what actually quantum computing is. So because the thing is, a lot of people think that quantum computing lies around designing algorithms and stuff like that. Like it depends upon the what I can say, doing some basic running some basic coding programs and stuff like that. So I'm like just going to break the myth that like quantum computing is a very much broad term. And the thing is, there is a lot of theoretical and experimental stuff which lies behind this. So it is not completely about coding and programming, but there is a lot of stuff in the back end which is important to study, like example quantum mechanics and classical physics, quantum physics, and lot of mathematical equations are very much important for someone to start their career in quantum computing. So that is why it is important to study the theoretical and the fundamental part of quantum physics, to just be just to have some uh, practical knowledge of what is quantum computing. So
okay.
yeah.
So yeah. So before we dive into like what quantum sensing is and um how one of its potential applications is quantum radar, like could you briefly just kind of just as an icebreaker, like talk about like what is as you might have been asked this question before, but like what is quantum physics? What are its major applications, and why is quantum physics so important, and like how is it fundamentally different from like classical physics?
Yeah. So actually, quantum physics is very important from the like point of view of quantum computing. And quantum physics, like, is also known as quantum mechanics, is a branch of physics that studies the behavior of matter at energy at a scale of atom and subatomic particles. And to tell you that why quantum physics is necessary, because quantum physics is very much important from industrial and the theoretical point of view. And quantum physics is important because it's provide a fundamental understanding of the behavior of matter and energy. And it has also led to many theoretical predictions and experimental discoveries. For example, quantum physics has many major applications for the development of uh, various communication protocols. For example, the BB84 protocols, which is very much useful for quantum communication. And quantum physics has led to development of new energy technologies such as solar cells and quantum thermoelectric devices. So I guess quantum physics is very much important because it provides a deeper understanding of the nature of the universe. Okay, so I guess it's very important to understand the nature of the universe, and it has practical application that will be very much useful to transform many fields. Like it has the major applications and the major potential to revolutionize that many fields of study, for example material science. So I guess quantum physics is a very much important thing to study right now. And just to explain what is quantum physics is, it's very much different than classical physics. So quantum physics is a branch of it is the same as quantum mechanics. It studies the behavior of energy and matter at subatomic and atomic level. So it describes the behavior of a particle at this level using a set of principles that are different from classical physics. For example, at the core of quantum physics is the particle principle of superposition. So like you might have heard about the principle of superposition. So principle of superposition states that a particle can exist in a multiple states or locations simultaneously. So that is why it is important to study this principle of superposition. And it has another what I can say, a principle which is called as quantum entanglement. So quantum entanglement is a phenomenon where the properties of two particles can become correlated even when they are separated by a large distances. So I guess both these things are very important for quantum physics. And that is why quantum physics is different from classical physics, because of because of the probabilistic nature of quantum physics. Because I guess quantum physics is unpredictable, and it's very much different than classical physics. And I guess quantum physics also very much weird, in the sense like it cannot be predicted, and it cannot be, we cannot say that it has a certain outcome. So that is why quantum physics is different than classical physics. And to explain it, I can share you example of why quantum physics is different from classical physics. So to explain it, have you heard of uh, uh, what I can say, the the famous experiment by Max Planck? So I guess you might heard of Max Planck, right? So Max Planck did an experiment in which he worked on quantum theory. So in which he did an experiment based on quantum physics. So the outcome of the research was that the particles exhibit a different nature. So he wanted to study the uh, uh, phenomenon behind this, and so he came upon like a weird interpretation of the particles. So that's he named it as quanta. So that's how like we were able to get into like a much explanation about what quantum physics is. So that is why like it is very important to understand quantum physics from a quantum computing perspective, and to like differentiate between quantum physics and a classical physics. There's a very much famous example from Schrodinger as well. So I guess Schrodinger also explained that the quantum superposition is also different from a very classical physics background. So it is very important to study quantum physics from a quantum computing perspective, and its major application is also uh, in quantum computing and quantum information and quantum field theory. So that is how why quantum physics is very much important.
Okay. And like, what are some of the mathematical principles behind quantum physics
Yeah.
and like all its
So
application?
yeah. So I guess quantum physics is basically built upon the foundation of mathematical principles and concepts, and it has very much in-depth mathematical equation and formulas. For example, I cannot go much into the depth of that mathematical part because it might take a lot of time. So I will focus on like four important part which is important for quantum physics. So first of all, linear algebra. I guess you might heard about linear algebra, right? So linear algebra is the mathematics of vector spaces, and it is used to represent quantum states and quantum operations. And quantum states are represented by vectors in a complex vector space, and quantum operations are represented by matrices. So linear algebra is very much important from a quantum computing perspective, and it is part of uh, it is the mathematical principle behind quantum mechanics. And very much linear algebra has very much bigger implementation in quantum computing. Like you can find a lot of applications in quantum mechanics of like from linear algebra. Like you like linear algebra has eigenvectors, eigenvalues, matrices, and a lot of stuff which are used. And other thing is the Hilbert spaces. So Hilbert spaces is a mathematical concept that is used to describe quantum states, and a Hilbert space is a complex vector. So Hilbert space is also very much important from a mathematical point of view, and it is implemented in quantum mechanics as well. And apart from that, there is operators. So operators are mathematical objects that act on quantum states to produce new states. So they are used to represent physical observables such as position, momentum, or spin. Okay, so after that, there is complex numbers. So quantum mechanics makes use of complex numbers to represent probabilities and amplitudes. And complex numbers have a real and imaginary part as well. And they are used to represent the phases and magnitudes of quantum states. So I guess this is the mathematical principle behind quantum mechanics and quantum computing. So to give you an overview, that mathematical part is very much what I can say advanced and very much broad. So I cannot give only four application, but there's a lot of mathematical equation behind quantum physics and quantum mechanics which cannot be covered into a single slide. So I guess there's a lot of things which are there in quantum mechanics and quantum physics. So the mathematical principles behind quantum mechanics are based on linear algebra, and there is also probability theory. I have not mentioned it in my slide, but the quantum mechanics is formulated using a mathematical structure known as Hilbert space. So this is a complex vector space equipped with the inner product, and that is used to describe the state of a quantum system. So the state of a quantum system is represented by a vector in this Hilbert space, which describes all possible outcomes of the measurement that can be made on a system. For example, the mathematical description of quantum mechanics also involve operators, which I told you earlier. So operators are something which act on the vectors to describe the evolution of the system over time. So operators are used to represent the physical observables such as position, momentum, and energy, and the outcome of the measurement. So these observables are given by the eigenvalues. So like if you want to know like how the eigen observables are calculated or measured, they are given by the eigenvalues of the corresponding operators. And another important mathematical principle in quantum mechanics is the wave particle duality. So this is very much important, and this principle is described by the wave function. So which is a complex valued function that describes the probability amplitude of finding a particle in a given location, and the wave function is used to describe the behavior of both particles and uh, what I can say the waves, and it's the central concept of superposition and entanglement in quantum mechanics. Like for example, there's a lot of mathematical principles and complex and abstract, and which are essential for understanding the behavior of matter, energy, and the atomic and the subatomic level. So that's about.
So, you mentioned quantum machine learning briefly earlier, and
Yeah.
I just wanted to know, like, how can you tie quantum physics into artificial intelligence? Like, what is quantum machine learning essentially? Like, if you could talk about that.
Yeah. So are you able to see my screen? So I guess I mentioned.
Yeah.
Yeah, yeah. So quantum machine learning, I guess, is a very emerging field that combines the principle of quantum physics and with machine learning, and I guess it's very new branch of quantum quantum physics, and it is very much exciting and very much new, and I guess like very much what I can say, it holds the potential to revolutionize the field of quantum computing, because there is a lot of thing which is still being worked upon, and quantum machine learning can give us some great results. So it's an active field of research right now, and it is very much new. So quantum machine learning is an emerging field that seeks to combine the power of quantum computing with the techniques of classical machine learning. So the goal of quantum machine learning is to develop a new algorithms and models that can be what I can say that can be used to predict or improve the efficiency and accuracy of machine learning tasks. For example, there is a lot of like classical machine learning models called as what I can say. For example, the quantum neural networks, uh, the generative adversarial neural networks, the restrictive Boltzmann machine. So there's a lot of quantum machine learning models which we can use, for which we can use quantum machine learning to improve the accuracy and the efficiency of the machine learning models. And the goal of quantum machine learning is to develop the new kind of algorithms and models that can leverage the unique properties of quantum systems to perform certain computation much faster than classical computers. Okay, so one of the main advantage of quantum machine learning is to potentially perform certain tasks exponentially faster than classical algorithms. For example, quantum algorithms can be used to for example, quantum algorithms have been developed for I guess quantum inspired classical algorithms and quantum enhanced classical algorithms and fully quantum algorithms. But however, quantum machine learning is very much early stages of development, so much of the research is still very much in the theoretical stage as now, which I have mentioned. For I guess quantum machine learning will be quantum machine learning will need a lot of work which need to be done right now, and there's a lot of stuff which is need to be done. For example, I guess there is a recent work which has been highlighted for quantum machine learning, which will be used in error correction. So for quantum machine learning to be used in quantum error correction, there is a lot of work to be done right now, and it is an active area of research. For example, algorithms have also been used to classically find out the uh, classification of various quantum data sets and quantum machine learning data sets. So I guess it's very much important to note that quantum machine learning will be used like efficiently in the future. So yeah.
So like how what so like the hardware used by like quantum computers is much different. So like could you just talk about like how do you integrate the software and the hardware like even in the case of like quantum machine learning or like do you use IBM Qiskit in order to
Yeah, yeah.
create programs? Like could you just talk about that a little bit?
How do we encode the hardware and software in Qiskit in quantum
Like how
computing?
do you
Okay.
yeah, like how is the software coded in the hardware like for a quantum computer? Like
Okay.
how is it integrated? Yeah.
Yeah. So I guess the integration of hardware and software in quantum computing is a very complex process. So, and the specific thing depends upon the quantum computing systems which is being used. However, in general, the process involves a lot of steps which are very much complex and are very much what I can say experimental. So first of all, you need to design and fabricate the hardware. So the first step is to design and fabricate the physical components of the quantum computing system, which is called such as the qubits and the control electronics. So this requires high expertise in fields such as material science, nanotechnology, fabrication, nanofabrication, and electronics and electrical engineering. So after we have done that, we need to develop the control software. So once the hardware is available, like software must be developed to control it. So this involves the designing and implementing algorithms that can be implemented and manipulated, and how this can be manipulated and implemented to perform quantum operations. So once we have developed the control software, then we move on to optimize the hardware and software interface. So the software must be optimized to work with the specific hardware platform, like taking into account the factors such as the physical properties of the qubits, the control electronics, like any noise or error resources. For example, you might be knowing that quantum computers fail due to noise, right, and to decoherence. So there is a lot of physical environment and environmental consideration which is taken into account before designing and before integrating the hardware into the software into the hardware part. So then after that we need to test and debug. So the integrated system must be tested and debugged to ensure that it is functioning correctly. So it may involve running a diagnostic test on the hardware and software, as well as benchmarking and validation experiments. So benchmarking is very much important here, and to improve and test the quantum algorithms, and after that we need to refine and improve. So after that, the hardware and software used, they may need to refine and improve after having the feedback from the team and from the customers or the clients. So the integration of hardware and software and quantum computing requires a very much expertise in field and deep understanding and principle of quantum mechanics, fabrication and electronics and stuff like that. And it's very much important to note that collaboration between experts in different areas is very much important. For example, this field is very much interdisciplinary. So to integrate the hardware into to software, a lot of people from different fields would be required. For example, we need mechanical engineers, we need the fabrication engineers, we need electronic and electrical engineers here. So the thing is, it is very much complex and very much a hard process to integrate the hardware into quantum software and to integrate the quantum algorithm into hardware. So yeah.
Okay. And so, like, kind of diving into the main theme for this episode of the podcast now,
Yeah.
like, could you talk about like what is quantum sensing, and then also eventually just talk about like what is quantum radar and like how it might be used by stealth fighter jets or other air forces around the world.
Yeah. So I guess quantum sensing is a technology that uses the principle of quantum physics to make highly precise measurements of physical quantities such as magnetic fields and temperature and pressure. So it is based on the ability of quantum systems such as atoms or electrons to behave in a coherent way and respond sensitively to external stimuli. So the benefits of quantum sensing include its ability to make highly precise measurements. For example, its ability to work in extreme conditions. And I guess quantum sensing it's a very much potential in for detecting undetectable signals. For example, quantum sensors can be used in medical imaging to detect subtle changes in the body that may indicate the presence of diseases and underlying any kind of ailments or anything. So also there are very much disadvantages and threat posed by quantum sensing, and one of the main concern is that it could be used to develop technologies for surveillance and espionage. Surveillance, and it can be used for developing various nuclear weapons as well, and it can be used in a negative way. So for example, it can be used to lead to a new arms race as countries compete to develop and deploy the most advanced quantum sensing technologies. And quantum sensing is also has application in quantum radar. So quantum radar is an application of quantum sensing that is been developed for military and defense problems, and it uses the properties of quantum entanglement to create radar signals that are much more difficult to detect and jam than traditional radar signals. So what actually happens in traditional radar is the signal is sent out and then bounces off an object, which reflects the signal back to the radar receiver. However, in quantum radar, two entangled photons are sent out instead of one signal, and when one photon hit an object, for example, one photon hits the object, the other photon instantly knows and reacts in a way that reveals information about the object location and other characteristics. So this allows for a stealthy detection of objects that might otherwise be invisible to traditional radar. So that is why a quantum radar is very much efficient over traditional classical radar system. And in military aircraft, quantum radar could be used to increase the stealth capabilities by detecting and tracking other aircraft or missiles like without being detected. So it can also be used to detect stealth aircraft or unidentified objects in the air. Like for example, if there is a missile or any rocket coming, like enemy infiltration or any invaders out there in the enemy territory, the quantum sensing and quantum radar technologies can be used efficiently to detect any incoming intruders, which can be safely avoided. And quantum radar can also be used for what I can say to detect the asteroids or comets, which is a threat to the human and to the mankind. So I guess in military aircraft and quantum radar could be used to increase the stealth capabilities by detecting and tracking aircraft or missiles without being detected. So it can also be used to detect the stealth aircraft or other objects that are designed to evade the traditional radar. However, the technology is still in the experimental stage, and it might take some time to deploy in practical applications. And to tell you that quantum sensing has many kind of different applications in uh, journal applications, which are also like can be used. For example, quantum sensing can be used for medical imaging. For example, quantum sensors can be used in magnetic resonance imaging (MRI) to detect subtle changes in the body, human body, that may indicate the presence of diseases. And quantum sensing can be also used for mineral exploration. For example, they can use to detect the mineral deposits of natural resources is deep underground, and they can be used for GPS navigation and environmental monitoring, and they can be used for astronomical purposes as well. They can be used to detect the faint signals from other galaxies and objects in space, such as gravitational waves and dark matters and black holes. So I guess quantum computing has a huge potential. Quantum sensing has a huge potential for research and technology, and it is an ongoing area of research right now. So, like there is nothing there are claims that quantum sensing can be used, but it is an active area of research right now. Like researchers are trying a lot to try out different things in quantum sensing, and I guess quantum sensing is also giving a new like it's making its way for different technologies as well. For example, quantum sensing is also connected with image processing, computer vision, quantum metrology. So quantum sensing is very much a new and a different field of technology which is taking place right now. So that's about quantum sensing.
But like, how many years would you think it would take before like air forces and military forces or like stealth aircraft fully embed the system into their aircraft and into their systems?
For what kind of application?
Like, for how many years would you think it would take for like quantum radar to be fully implemented in military aircraft? Because right now you're still like in the experimental stage.
Yeah, yeah, yeah.
But like, how many years do you think it would take? 5 or 10 years?
So I guess it is difficult to predict the exact timeline for the development of quantum radar for military use, because I guess it depends on various factors such as funding. So funding is very much important, and the research progress and the technological advances. So I guess all these factors, like combined factors, are will be taken into consideration to actually say how much time do we need and how much time it will take for actually getting quantum radars for in actual practice. So I guess it's very much important to note all of this, and there have been reports that successful demonstration of quantum radars is there in like I guess I've heard some news that actually it has been successfully implemented, but I don't know like it if it's true or not. But I have heard that some laboratories have successfully demonstrated the quantum radars in laboratory setting, and some experts predict that practical application may be possible within the next decade, like within the next 10 to 5 like next 10 to 15 years maybe. So I guess that the development of quantum radar for military use is likely to be subjected to regulatory and ethical consideration, and the technology may be subject to export controls or restriction, because you might be knowing that quantum sensing and radar technology can be misused. So it will be subjected to many much restrictions and a lot of laws and things like that. So it will be taking some time actually to implement all this. So
Okay.
yeah.
Yeah. Yeah. Yeah. Those were all the questions I had that I kind of wanted to know about like quantum sensing, and in particular, I wanted to know how it is applicable, especially to the aerospace industry. And to me itself, like it is just mind-boggling how you can, tie quantum physics and tie like quantum sensing into aerospace engineering. That itself really, I'm simply amazed by it. And yeah, I just really would like to thank you for taking the time and creating the presentation and accepting my invitation and coming on the podcast. And you have a LinkedIn page as well, which I'll link in the description of the video later when it is published. And I would just like to wish you the best with your research.